Here we go. The D flip-flop, and this is Q next. If you recall, we said if D is 0, what is the next state going to be? 0. If Q is 1, what's the next state? 1. Regardless what the previous state was. That's the D flip-flop. That's an old one. We went through some of these flip-flop and we list them. The SR flip-flop. And Q next. If S is 0, R is 0, we said the next state is what? Whatever the previous state, Q previous. 0, 1, that's set, reset. Reset, that's a 0. 1, 0, that's a set, that's a 1. And 1, 1 was what? Not allowed. The JK flip-flop. I'm just summarizing all the flip-flop. If it's 0, 0, that's the same as SR. That's Q previous. 0, 1, that's a 0. 1, 0, that's a 1. And the difference when it's 1, 1, that's the complement. And the T flip-flop, that's a toggle flip-flop. Has only one input. When T is 0, what happens? Everything stays the same. When T is 1, you toggle, you complement the previous state. And now what I'm going to do, create what we call excitation table. The excitation table, if I know the current state and the next state, can you tell me what J and K should be, or S and R should be? So I'm going to do it for all of them, and we're going to use that. Here we go. So this is the current state. This is the next state. And let's begin with the first flip-flop we'll look at. Maybe we'll do the D flip-flop. What does D should be? So 0 to 0, 0 to 1, 1 to 0, and 1 to 1. These are the 4 scenarios. Let's look at the D flip-flop. If the next state is 0, what is D going to be? 0. So it's 0 here and 0 here. And for the next state to be 1, D will have to be what? 1. So that's what D should be to go from here to there. Let's do the J and K. This is J, and this is K. Let's see what J and K should be. From 0 to 0. Well, that's the same, right? That's this case. From S to go, so it could be staying like this. You could have 0, 0. That will give me the same thing, or what? If it's 0, 1. So as long as S is 0, oh, I'm looking at JK, I'm sorry. I want to do SR. I'll put them in order. Doesn't really matter. But I'll go in order the way I list them up there. Since I list them in that order. From 0 to 0, I can accomplish that by making it 0, 0. S is 0, R is 0. or 0, 1. That will force the result to be 0. So as long as S is 0, and don't care what R is. Zero to 1. 0 to 1. I can't do that with 0, 0. I can't do that with 0, 1. So it has to be what? 1 and 0. That's the only way to go to 1. Because this is not allowed. 1 and 1 is not allowed. So as long as you have a 1 here and a 0 there. 1 to 0. I can't do it with 0, 0 because 0, 0 will make it a 1. 0, 1 will make it a 0. So that's what? 0, 0, 1. And what about 1 to 1? Well, to go, no, from current state to next state. I can do that if I put 0, 0. I'm not changing the state. And the other option, if I do what? 1, 0. So as long as R is 0, and don't care what S is. The next one is the JK flip-flop. Let's look at the JK. To go from 0 to 0, keep it the same as long as J is 0 or K is 0. Or 0 to 1. So J has to be 0 and K don't care. Zero to 1, that's a complement. I can do that if I put 1, 1. It complements that. See it? Or if I put what? 1, 0. If I put 1, 0, it's going to make the next state 1. So as long as J is 1, K don't care. 1 to 0, that's also a complement. I can put 1, 1 here, that will complement that. Or 0, 1. So as long as K is 1, don't care what J. And the last one, from 1 to 1. You can accomplish that by putting 0, 0, that will keep it the same, or putting 1, 0, 1, 0, that will force it to be a 1. So as long as K is 0, J don't care. And let's look at the T flip-flop, 0 to 0, no change. T will have to be 0. 0 to 1, that's a toggle. T is 1. 1 to 0, that's a complement. T is 1. 1 to 1, that's the same. T is 0. This is called the excitation table for the D, the SR, the JK, and the T flip-flop. We need to know this when we're doing state diagrams. I'll print this, I'll have it nice and neat, and I'll give it to you. Hopefully next class, if I remember to bring it. I already typed it and printed it, actually. I just forgot to bring it. Printed one copy. I shouldn't say printed. Printed one copy. I just got to make copies of it. So I'll bring that next time. It's called the excitation table. So how do we use that in our design? Let's take a state diagram and go through the process from top to bottom. Let me save this paper. Save them. Okay, let's say we have this state diagram. We have 4 states and they are labeled 0, 0, 0, 1, 1, 0, and 1, 1. If my input is 0, stay there, my output is 0. If my input is 1, I go to this, my output is 0. If my input is 0, I go right here. My output is 0. If it's 1, I go here. My output is 0. If it's 1, I'll stay here. My output is 1. If it's 0, I go back here, and my output is 0. If I'm at this and I put in 0, I go right here, my output is 0. If I put in 1, I go down here, and my output is 1. Let's say this is the state diagram that I have. So the first thing, I'll wait till you finish writing, is we need to know how many states do we have. Don't we have 4 of them? So what's the number of flip-flops? How many flip-flops we're going to use? Can't be 1. Remember, 2 to the power of n has to be greater than or equal to the number of states. 2 to the power of n. N is the number of flip-flops. So we need a minimum of 2 flip-flops. That's why we're using 2 digits. So let's decide what kind of flip-flop we're going to use. Here's our choices. D, S, R, J, K, T flip-flop. Which one? J, K, since nobody answered? Because more work. I'll do the J, K. So we're going to use J, K flip-flop. I used the SR last time, I think. Did I use SR last time or JK?
No, JK.
Let's use SR then. Yep, SR, since I used JK last time. SR flip-flops. I need 2 of them. So if I go to design them, build them, here's my design. I'm going to have 2 flip-flops. That's the first and the second flip-flop. This is the first one. We'll call it S1 and R1. This is S2, second flip-flop, and R2. This has 2 outputs, Q2, Q2 not, Q1, Q1 not, and there's a clock here attached to both them. To synchronize everything that we need. CLK, clock. And the question is, what are you going to attach to S and R, S1 and R1, S2, R2, to actually give me that diagram? Also, we have an output here. If you remember from the state diagram, we have an output. So let's see. I'll wait till you finish writing the stuff. Let me go back here, and let's create the state table for this one. I'll leave this one here. Here's my state table. I have Q1, Q2. I have my input, which we'll call it X. So my combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, and 1. So these are my inputs. So these two are the current states, and X is your input, the external input. Q1 here, star, and Q2 star are what? The next state. And we're going to have Z, which is what? Output. Let's go through them. If I'm a 0, 0, and I put in a 0, I stay there. And what's my output? 0. If I put in a 1, I go to where? 0, 1. My output is 0. If I'm at 0, 1, I put in a 0, I go back to 0, 0, my output is 0. If I put in a 1, I go to where? 1, 0, my output is 0. If I am at 1, 0 right here, and I put in 0, I go to 0, 0, my output is 0. If I put a 1, I stay there, and my output is 1. And the last one, if I'm at 1, 1, I put in a 0, I go to 0, 0, my output is 0. But if I put in a 1, I go to where? 1, 0, my output is 1. So this is the state table. Now we went from state diagram to state table. Next now, I need this one back in. I'm using SR flip-flop, right? So this is S1, R1, this is S2, R2. And it would be nice if I use color coding here just to see what I'm looking, because I always lose track of where I'm looking. For S1, R1, I have to look at this column. Can you see the yellow there on the screen? With this column. Where I am, where I need to go. From 0 to 0, the first three of them, 0 to 0. Well, 0 to 0 with SR should be what? 0 and don't care. Can you see it, everyone? So that should be 0, don't care, 0, don't care, 0, don't care. 0 to 1. 1 and 0. Next one, 1 to 0. 1 to 0, SR is what? 0, 1. 1 to 1, don't care and 0. 1 to 0, 0, 1. and 1 to 1, don't care, and 0. The second flip-flop, I need to look at this column with this column. So let's look at these colors. Again, the yellow here, the result of the yellow, so I'll highlight them to match. Let's look at that pink from 0 to 0. S and R means what? 0 and don't care. 0 to 1. That's 1, 0. 1 to 0, 1 to 0 twice. 1 to 0 is what? 0, 1? Twice. 0 to 0 twice. 0 and don't care. And 1 to 0 twice. Where's 1 to 0? 0, 1, 0, 1. Now I have to do a K-map for each one of these and also for Z. Each one of these to see what's attached to them and Z. And once I finish with the K-map, I'll come back to this and build my circuit right here. I probably could fit them here, so I'll try to fit them there. I'll try to be a little bit neat here. So I have two inputs here, Q1, Q2, and X. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. I'll do the same thing. I could probably fit three of them on one line, but that's okay. This is Q1, Q2, and X. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Let's make that for S1, and let's make this one for R1, and see what the expression for it. Let's put the values. 0, 0, 0, 1, 0, don't care, 0, don't care. And to group that, probably the easiest thing is what? Right here, the best group. And that will make it what? Q2, X. Do you agree with that? What's R sub 1? XX, X0. 1, 0, 1, 0. Best group for this one? Right there. X bar. 4 of them. Now let's do one for, I don't need to go that far, So maybe I can shrink the size. Here we go, Q1, Q2, X, and this is for S2. We'll do another one. For R2, I crooked already. Q1, Q2X. This is for R sub 2. And we need one for the output here. Every time I do this, I should just have one of those sheet made already with these in it for different sizes, like 4 by 4, like 4 variable, 3 variable, have them made so I don't have to spend time just labeling these, just go through them. Then I leave the room and the third leaves my mind. And this is actually for Z. So let's look at S2, 0, 1, 0, 0, 0, 0, 0, 0. You don't have a choice here. It's Q1 bar, Q2 bar, X. R2, X0, 1, 1, XX, 1, 1. How about these four? Q2. And now let's go to Z, 0, 0, 0, 0, 0, 1, 0, 1. Q1, X. And now I got everything ready. I just got to attach them right here. Everyone's done writing? Now let's attach them. We have one external input, that's X, so let me put X here. Let me do the knot here, so I'll have the knot of that if I need it. Okay, what is going to S1? Q2 and X. It's an AND gate. It's an AND gate. And Q2 and X. This is X. Attached to X and attached to where? Q2. That's Q2 and X. R1, what's attached to R1? X1 bar. Q1 bar, Q2 bar, and X. That's attached to S2. So let's do an AND gate. Q1 bar.
Yeah, you miswrote it. It's supposed to be right on the left one is Q1,
Q1 on top.
Q2 bar, or Q1 bar.
In the flip-flop.
In the flip-flop?
On the
On
diagram.
the left.
Here?
Yeah.
What did I miss?
Q1 on top.
Oh, the one here? What did I miss?
The top Q's not bar.
The top.
It's not a Q bar one, it's just.
You had
Q.
two.
They're not.
Oh, Q2.
Never mind.
No, just in the diagram, you had Q bar.
Oh, I see, I see. I call them Q bar here on both these. Got you. Thank you. Yep, okay. Yeah, one's Q1, the other one Q1. It can't be the same. So now let's see. Let's look at this. Here's Q1. Q1 bar, Q1 bar, not Q. So I gotta take one from here, I gotta take one from here, I gotta take X. I probably could sneak the X from here. I should make that gate a little bit bigger, but that's okay. That's X. That's the first one. I have Q1 bar. Go into that. And I got a Q2 bar. I can pull that from the bottom here. Wrap it around. And what about R2? That's Q2, right? That's R2 now. And finally, what do we have? Z, the output. Here we go. It's an AND gate. And there's two inputs, Q1 going to it and X. This is X going to it, and the other one is Q1. And that's the circuit now. That will give me the state diagram. So give this to somebody to build it, or you go to the lab and build it. And as you're playing with, you start, for example, with 0, 0, you start playing with X and see what will happen. You'll see the light goes on and off, going from state to state. Now this wasn't a bad one to deal with. Let's see if we can sneak another one. Let's see if I can get a bigger one quickly. I don't know if I have time for a bigger one in this video. I might have to wait till next time, but I'll do one. Let me take a smaller one for now. Okay. Here is one. Try to get one I can do in like 10-15 minutes. And we have state A. I'll put 0 for that. When you put a 0, you stay here. When you put a 1, you go to state B. Your output is 0 at state B. You put a 0, you go back here. You put a 1, you go to this one, state C. You put a 0, you go right there. You put a 1, you go another state, state D. D, you get a 1 for output. You put a 1, you stay here. You put a 0, you stay here. Different example. How many states do we have? 4. How many flip-flops? We want 2 to the power of n to be greater than or equal to the number of states. So n must be 2. 2 flip-flops. Let's use, I don't know, D flip-flop. It'll be less work. There's only one input, so I only have to do one map for each one. So now I got to go to my state table here. So I'm going to label state A as my state Q1, Q2. A will be 0, 0. I'm going to label A at 0, 0. I'm going to label state B as what? 0, 1. I want state C to be 1, 0. State D to be 1, 1. So that's what I'm going to use for labels. Okay, here we go. Current states. Current state we have what? Q1 and Q3. Your input, the next one, we have X. Q1, Q2, 2 states.
So you got Q3 over there.
I can call them Q1, Q3, but really Q1, 2. As long as I don't put Q1, Q2, Q3. So 0, 0. If I'm a state 0, 0, and I put a 0. While we at it, let's finish where we're gonna go. So this is the next state. Which is Q1 star, Q2 star. We're also gonna have the output. I don't know why I call my output always Z. Maybe it has something to do with my name. So if I'm at 0, 0 right here and I put a 0, I stay there, my output is 0. But if I put a 1, I go to state B, which is what? 0, 1, my output is a 0. If I'm at 0, 1, state B, and I put a 0, I go to A, which is 0, 0, my output is 0. But if I'm at 0, 1, I put a 1, I go to state C, which is 1, 0, and my output is 0. If I'm at C, which is 1, 0, and I put a 0, I go to state A, which is 0, 0, my output is 0. But if I put a 1, I go to state D, which is 1, 1, and my output is 1. And if I am at state D, and I put a 0, I go to state 0, 0, my output is 0. But if I put a 1, I stay there, and my output is 1. So that's my state table. Now we decided to use what kind of flip-flop? D flip-flops. So this is D1 for the first flip-flop. This is D2. The D flip-flop has only one input. That's why I like the D and the T flip-flop. One input. Where's my excitation table for it? This is the current state. This is the next state. Here's the good thing about the D flip-flop. D is always going to be the same as the next state. That's why it's called data flip-flop. See it? When this is 0, D is 0. When the next state is 1, D is 1. So basically, your D for 1 is going to be all these values. 0, 0, 0, 1, 0, 1, 0, 1. Doesn't matter what the current state is. But you can look at the excitation table if you want to do it the other way. And Q2 here, and this is what D2 is going to be. Zero, 1, 0, 0, 0, 1, 0, 1. Done. I just got to do a K-map for D1, a K-map for D2, a K-map for Z. 3 of them. Question? No? D and T flip-flop are really popular because it makes it quicker. You don't even have to look at the excitation table. I can mix and match. I can make one of them D and the other one T. You're going to see me next class, instead of using K-map, I might say, let's have fun with it. Let's go back and use a multiplexer for input. Let's use a decoder. I'll do that next class. So this is for, let's make that for the output Z. And I'll do one just like it for D1 and D2. Q1, Q2X. That's for D1. And let's do one more for D2. Q1, Q2X. D2. Let's begin with Z. 0, 0, 0, 0, 0, 1, 0, 1. What do we have? Q1X. Let's look at D1. 0, 0, 0, 1, 0, 1, 0, 1. This one, this one. This is going to be, the first one is going to be what? Q1X. What do you know? I can use the same gate for both these. See that? Plus Q2X. By the way, if you just looked at the Boolean algebra, because that's and, or, right? And, or, you could minimize that by factoring X out. But if you factor an X out, then you have to build one for this one. So you really didn't save anything. But if I didn't have this, I would have factored an X out. It would be X ANDed with Q1, Q2, one AND, one OR, instead of two ANDs and one OR. But then if I do that, I have to build one for this. I'm still two ANDs and one OR. What's D2? 0, 1, 0, 0, 0, 1, 0, 1. Oh, what do you know? Same gate. Q1X. And for this one, I'll take this and that, and that'll be what? Q2 bar X. This is actually good. It shows up in 3 places. Same gate I can use for all 3 of them. So now let me build the circuit. Two flip-flops. Each one has one input. So this is the first flip-flop, has one input, we'll call it D1, has 2 outputs, Q1, Q1 not. Another input here, D2, 2 two outputs, Q2 and Q2 naught. There's a clock going to both of them to synchronize them, make sure everything toggles at the same time. And let's see. I have one input that's X. This is the complement of X, if I need it. And what is going to D1? Q1 and X. Let's make an AND gate.
Oh, that was Z.
Oh, that's Z. It's also going to D1. It's going to all three of them. Right? So let's look at, you want to do Z first? Well, let's do D1 first. I have an OR gate. And to the OR gate, I have two AND gates. Here's one AND. There's another AND. The first AND, is Q1 and X, right? So this is X. And this is Q1. And the second one, Q2 and X. So we can do Q2 and X. Q2 and X. That's the first one. An OR gate with two AND gates going to it. D2, an OR gate with, again, two AND gates. But one of the AND gates is right here. We already have it. That's the Q1 and X. And what about the other one? Q2 and X, right? So I can do another AND gate here. And what's going to it is Q2. And X. X is way on the top. I can grab it from up there. And the last thing, what's Z? Z is coming out of this, right? That's Q1X. That's what Z is. Just extend the cable, and that's where your Z is. Attach it right there. So this will decide if the door should open and the candy bar should drop out or not. If Z is 1, the door is going to open quickly, a candy bar will drop, the door closes. And this will decide where the next state to be. Now, with all these, I made it simple enough. All of these. You're going to see next time we'll do our own design, which probably going to take 2 classes to do, or maybe 1.5, if I decide to tackle a soda machine. Because when you look at that, you'll see how many input. Like it's so just a soda machine when you can 5 cents, 10 cents, 25 cents. If we just thought about that, I'll just show you why it might be ugly. Not it might, it will be. Let's say it's one soda, even one type of soda. What's the price? 35 cents? Let's make it 35 cents, because if you make it more than 35, it gets even worse. Your input, 0 cents, nothing, 5 cents, 10 cents, 25, no 50, no dollars, nothing. If you just tackle that, well, I don't want to do it. Here we go. Watch this. This is the 0 cent state. This is the 5 cent state. This is the 10 cent state. This is the 15 cent state. This is the 20 cent state. This is the 25 cent state. This is the 30 cent state. No, 35. If you put a 0, you stay there and you get no money. No candy, I mean. No candy and no change back. You have 2 outputs, now you get candy and change back. If you put 5 cents, no candy, no change back. If you put 10 cents, no candy, no change back. And if you put 25 cents, no candy, no change back. If you have the 5 cents and you put nothing, no candy, no change back. 5 cents, no candy, no change back. 10 cents, no candy, no change back. 25 cents, no candy, no change back. If you have the 10 cents, you put nothing, you get nothing, nothing. 5 cents, 10 cents, you go 20. What about if you put 25 cents now? You got to go back, reset the machine. Give you what? 1 candy and no change back. If you have the 15 cents, you put nothing, nothing, nothing. 5 cents, you go right here. Nothing and nothing. 10 cents, how can I, let's see. Nothing and nothing. But if you put 25 cents, go back there. Now what do you have, 40 cents? You get a candy and 5 cents back. You put nothing, you stay there. You put 5 cents, you go there. 10 cents, you go here. 25 cents. You get what? Candy and how much back? 10 cents. You put nothing here, you stay there. 5 cents, you go here. 10 cents, you go here. And how much candy and what, 5 cents back? Oh no, no change back. No change back at 35 cents. And if you put 25 cents, you get a candy and 15 cents back. And if you here, you put a 0, you stay there. 5 cents. Candy, no change back. 10 cents. Candy and 5 cents back. And 25 cents. Candy and how much change back? 15 cents.
You're at 10.
That's a 10.
Oh.
So you got to design something like this. Now it seems ugly, but when you look at it, really, how many states do you have? 1, 2, 3, 4, 5, 6, 7. How many flip-flops you need? About 3.
Oh, 2.
2 to the power of n
Oh, yeah.
has to be greater than or equal to 7. If n is 3, what's 2 to the third? 8. Is that bigger or equal to 7? Yes, 3 flip-flops. The problem with that is you have change back, you get change money in. So your input are the 3 flip-flops, Q1, Q2, and Q3, but that's not enough. What are you putting for money? So you have a code for the input, X1 and X2. X2, if you put 0, 0, that's no money. If you put 0, 1, that's 5 cents. If you put 1, 0, that's what, 10 cents? If you put 1, 1, that's 25 cents. So you get Q1, Q2, Q3, X1, X2. How many? 5. 5 inputs. How do you do a 5 input K-map for each one?
2 K-maps.
2 K-maps for each one. And here's the bad news. Let's say you do JK flip-flop. You get 2 inputs for each one. You get 3 states. 2 times 3, which is what? 6. You need 6 of them. Each one 2 K-map. That's 12. That's not enough. What else are you getting back? Candy. That's 2 more. What about change back? Right? So Z1 and Z2 for change back. 0, 0, you get no change back. 0, 1, you get 5 cents back. 1, 0, you get 10 cents back. And 1, 1, you get what? 15 cents back. So your design now is going to be massive because you have 2 4x4 K-maps for each one of these. Q1, Q2, Q3. That's 6 of them. 2 for each one of these. 6, 8, 10. I have my candy, 12. 12 4x4 K-maps I got to do. 12 of them. And attach every one of them.
I could do the same thing in like 20 lines of code.
What is it?
That's why I'm a computer science major. You could do the same thing in like 20 lines of code.
Well, that's why you now program it, and you go, I'm not going to design this by hand. Plus, notice you only have one output. What about if you have multiple output? Like, I want Coke, Diet Coke, 7-Up, Diet 7-Up, Pepsi, Diet Pepsi, I don't know, orange drink. What about if you put 50 cents? What about if you put $1 there? I know it's not 35 cents. If you're not putting 35 cents, guess how many more states you're going to have? If it's $1 there for the drink, 35, 40, 45, 50, 55, 60, 65, 70. So you have a massive design.
It's all hard coded too. Like, what if you want to increase the price of the soda?
Yep. Then you got a problem with this. You got to go buy another device, another board, and redesign it.
All your life every day.
But I just don't want you to think it's always a simple, straightforward. So if the problem gets ugly, that's why we go to programming now. So you know what? I'll write a code for this. I'll look what the input is. Based on the input, I can tell you what the next state is. If the input is 5 cents, add 1 to this, or make this state equals, the balance equals balance plus 5. If the input is 10, balance equals balance plus 10. If the input is 25, balance equals balance plus 25. Once balance equals $1, give them a candy, and if it's more than $1, subtract them, give me the change back. Much easier with color if statement. But that's what we used to do. What killed us too, people became creative. Like they start getting like a piece of metal, cutting money the size, circles the size of a quarter, size of a nickel, size of a dime, and drop them in. Go to Chuck E. Cheese, get these tokens, put them in as quarters. Now the Canadian money is not worth as much as the US money now. If you use Canadian money, the machine spit it out. The machine knows that's not US money. They measure the resistance of them. They're different values. When you put the money, calculate what the resistor value for that one. If it's not this number, boom. Next time you're in the lab, take a wire, measure the resistor of a quarter, US quarter, Canadian money. You'll see it's not the same number. So you can tell if it's US money or not.
So you could just cut out a piece of metal of the same resistance.
Well, you could. You could.